math teacher claims that she has developed a review course that increases the scores of students on the math portion of a college entrance exam. Based on data from the administrator of the exam, scores are normally distributed with a population mean mu of 511. The teacher obtains a simple random sample of 1,800 students and puts them through the review class, and then finds that the mean math score of the 1,800 students is 518. That's talking about X bar, with a standard deviation of 116. Your null and alternative hypotheses always talk about mu. You always have equals in the null, so that narrows that down to choice A or choice D. Between those two, choice D would be a two-tailed test, claiming that it just makes a difference. It could make their scores lower. She was claiming that it would increase, improve, make greater than 511. Test the hypotheses at the 0.10 or 10% level of significance. Is a mean math score of 518 significantly higher than 511? So our test statistic. Remember, that is in the numerator with parentheses around it, X bar minus the claimed mean in the null hypothesis. So we would have 518 minus 511 divided by parentheses around S over square root of N. So 116 divided by square root of 1,800. To 2 decimal places, that's going to round down to 2.56. Now you can't see it, but on the question ID here, there's a dash T. That means that the online homework system is expecting that we use technology. And there's a good reason for that. Since the sample size was 1,800, that would mean 1,799 degrees of freedom, and that's not on the table. So either we could go with a more conservative approach using the 1,000 degrees of freedom, or even the z-score. Notice how some of these are really close. Some of them are exactly the same. Others are within up through here, if not the same, 1 or 2 1,000ths apart. And then they get a little further apart the further we go. Maybe as much as 9 thousandths apart. But with that dash T, I'm expecting to use technology. We rounded to 2.56. So I would use Tcdf. This was a one-tailed test. If it was a two-tailed test, I'd have to multiply by 2. Now in my earlier drawing, let's check that out. Plain mean was 511, which would match up with a t-score of 0. The sample had an X bar of 518. We just calculated that that would give us a t-value of 2.56. We're trying to find out if that puts us in the area that is the top 1/0 or 10%. Are they back here, which would not be so surprising, or are they extreme? Are they unusual? When we have assumed that 511 is what is true for the population mean in the null hypothesis. So, based on that drawing, I have a finite lower bound of 2.56. Try that again. 2.56. Keeps on going to the right to infinity, putting in the largest number that the TI-84 can handle. The sample size was 1,800, so there are 1,799 degrees of freedom. And this is what we're coming up with, a probability, which to three places, the two right after that in the 10,000th place would round that down to 5 thousandths, 0.005. And that 5 1,000ths is less than 0.10. 0.10, let's see. That would be 100 thousandths, and 5 1,000ths is less than 100 1,000ths. Yes, this is significantly higher. So the conclusion is that we have statistically significant results here. However, is that 7 points going to make that much of a difference? Is it practically significant? Now, let's see here. Seven-point difference out of don't know how many points there were, but I'll compare it against the mean. That is rounding to 0.0137, which as a percent be that. It may be that 7 points more on a test is not making that much difference, practically speaking. And it looks like they agree. So let's see here. Looks like this is the last part. What if testing at the same significance level, we only had that information from 350 students instead of 1,800? That's going to make change in the t-value, 350 students. So that lowers it to 1.13. P-value now. Well, let's do this. Same kind of drawing, except I'm looking at 1.13 for the finite lower bound. Oh. And since there were 350 students, then we have 349 degrees of freedom. So to three places, that will round up. The 6 is going to make the 9 go to 0, carrying that over, 0.130, which is worse than what we had here. Now, we would not have statistically significant information, and we would fail to reject the null hypothesis. So before we take a look at this, let me show something on the board. So we have that T is equal to X bar minus mu, or you could write mu sub 0 for the claimed mean and the null hypothesis. All that over all of the mini fraction s over square root of n. As n gets bigger, square root of n is also going to get bigger. If you're keeping all the rest of that the same, then s divided by something larger, that's going to give us that mini fraction is smaller. Because again, we're keeping all the rest the same. S is the same, x bar is the same, and the claimed mean is the same. Well, if we're dividing this by something smaller, then t is going to get larger. The larger sample size is going to give you a greater value of t. I should say this because x bar could have been less than mu and t could have been negative. The absolute value of t will be what is getting larger. That means we're pushing out into the tails. We're getting something that is more extreme, more unusual. And so there would be a lower probability of that, which would then make it more likely that we're going to reject H naughts. Now, what we just saw was the reverse of that. We saw a lower value of n, and we switched from rejecting H naught and finding statistically significant evidence for the alternative hypothesis to, with a lower sample, something where we failed to reject H naught, and we did not have something statistically significant. So, as n increases, the likelihood of rejecting the null hypothesis increases. However, large samples tend to overemphasize practically significant differences. That goes back to something we were looking at earlier with just a 7-point difference in the scores. Should be that it was practically insignificant. Choice B, and they agree. Okay.